morning, everyone. Great Wednesday, huh? You doing good today? Good morning. Let's see. Get everything all lined up here. I think we're ready to go. We got kind of a mishmash of topics to cover today because we're a little bit out of sync with the modules as a result of meetings I've had and holidays. And so I was looking at our list of topics and I went, oh, there's a few things that we actually didn't get to, in part because I was doing reruns of previous semesters. And so I think today will just kind of be kind of a catch-up day. And then if we have time to talk about the new stuff, the stuff that is the current topics, then we'll see how far we get. So let me show you what I got on our list of things to do today. Go ahead and stop the music. There, that's enough. Well, my iPad is doing its thing again where you can't see its video. There it is, I think. Let's see, there, not that one. There we go. Okay, so we got the 4 topics here. The first one I want to talk about is like find out where did my program crash? You're writing a program and it just seems to have crashed. It's got like a segmentation fault and you want to know what happened to it. Why did it do that? Next we need to talk about command line arguments, memory allocation, very briefly on memory allocation, not too much on that. And then if we get to it, we'll talk about files. And so I had put down as like the main topic of today was files, but then I realized that all these other things we need to kind of get out of the way first. So let's just get started. But while I get things set up, do you have any questions for me? Not much, huh? Okay, so I'm going to write a program that is going to deliberately crash. Now, can you tell me some ways that you, in your experience, have caused programs to crash? And then we'll try to replicate that behavior in this program. So have you seen any programs crash with like a segmentation fault or something else like that? What caused it? Or not what caused it, but yeah, do you know, I guess what caused it?
Well, trying to access something with a pointer that's null.
Okay, so null pointers are good. Let's see, what can we do there? One common thing, not one common thing, but one thing that I see some people do is we learned about pointers, and we have certainly said that if you have something like an int pointer, it points to an integer. But that's not, that is true, but it's not like the entire truth. It's not the entire picture, if you will. So if I do something like int pointer, let's call it p, then I have a variable called p, and the box there represents the memory set aside for p. And we say that, you know, p basically points to an integer. The thing is that there is the integer pointer, but then there's the integer itself, the thing that it points to. So when you allocate an integer pointer, it does not set aside space for the integer that it's pointing to. It just sets aside space for the pointer itself. So containing this box is just the memory address of an integer, but by itself, the declaration of an integer pointer does not set aside space for the number, right? The actual integer. So if you want to have like the number 54 off in some other memory location and this one points to it, then you really need to do two things. You need to have the integer itself, let's call this number, and then the pointer that actually points to it. So two things you need to set aside. Now, you can have a pointer that doesn't have a name, like you could have, just like the address of num. In that case, you've got a pointer that points to num, but it itself doesn't have any space set aside for it. Okay, so that's the important thing there, is that when you declare a pointer, it does set aside space for the pointer itself, for the address, but it does not set aside space for the thing that it's pointing to. So let's see if we can replicate that. Let's go like int pointer p, and then let's try to see, what can we do? We could maybe, let's go ahead and just ask the user for some input. Now, when you call scanf, you're going to pass into it a pointer to the integer that you want to have altered by scanf. And you might look at this and go, well, I've got an integer pointer, so I'm just going to put p here. I don't have to put the ampersand in front of it because it's already a pointer. And then let's go ahead and print it out. And here we do want to print out the number that p is pointing to. So we'll put a star in front of that because we want to see the actual number itself and not the address that's being stored. Okay, we'll go ahead and run this, and please enter a number. Let's put in 54, and then it crashes. So we want to find out, why did that crash? What happened? So how to find where my program crashed. So we're going to use the debugger, but we'll use it from the command line, and we really only want this one piece of information. Where did my program crash? That by itself could be really useful information. So to do that, you'll need to compile with the -g flag, and that tells the compiler to insert into the executable little tags that let it know which instructions correspond with which lines in the source code. Then you're going to run the program, let it crash. This will generate a file called core, which is right over here. We got a file here called core, and that contains a snapshot of the computer's memory at the moment that your program crashed. So we're going to use the debugger to analyze that core file and let us know what was going on when the program crashed. So the command you'll type in is gdb a.out core. So that, let me fix this typo here. So that lets it know, that tells the debugger to look at the a.out executable and also match up to it the core file that was generated. Let's go and take a look at what it does. Oh, I need to recompile this first. Now we'll let it crash. And then we'll do this debugging step, gdb a.out core. And it shows you a little brief, what we would call a splash screen here. So we will continue. And it says here, program was terminated with signal sig segv. So that's a segmentation fault. It's a here's segmentation violation, and this is called a signal. So programs can send back to, can issue what are called signals to let it know that, say, something happened, some event happened, and it sends a signal out to the operating system to let it know that some event happened. And it says here that the program crashed on line 1895 of fscanf internal.c, which is not a function that I wrote, right? It's actually crashing internally inside of what essentially is the scanf function. So that may be some information you want to know. You can say like, well, I didn't write this function, but at least I can see that it's crashing in scanf, and there's only one scanf in my program, and that's this one here. So it must have crashed on line 7. But you can also find out what part of your program called this. So we're crashing inside of scanf, but what line of my program actually invoked scanf? So at this time you can type BT for backtrace, and it shows you the call stack. Up here at the top of the call stack is scanf. The next thing down is something called, C99 scanf. And then here below it says on main at line 7 of crash.c is where the line in my code actually crashed. So this is important information. Even if you get nothing else out of this report, getting what line on your function this program crashed could be really important for you. Let's go over here and write down if it displays, I'll rewrite this here. Use the BT command to view the call stack. So here we see from the report that we crashed on line 7. It doesn't tell us exactly what was wrong, but it does tell us at least what line number caused this problem. Now, if you're curious and you want to dig around a little bit, of course we can hook this up to the debugger that's over here. But from the command line, and I'll have to tell you, I grew up using the debugger on the command line, so I'm at least comfortable enough to be able to do things like inspect variables, step through lines a few times. And if you want to inspect a variable, you can type print and then the name of the variable. In this case, p is the only one we have. Oh, it says no symbol p in the current context. Oh, the reason for that is we are inside of scanf, and there's no p variable inside of scanf. So I think we can type up to go up the stack, and then go up again. And now we're inside of main, and now I can print p, and it says the value of p is 0. The value of p is null, and so that's causing our problem. Okay, so a couple of commands for GDB. We already saw BT for showing the stack, call stack. It's called backtrace. Print and an expression. and then up, go up through call stack. And then you should probably also know Q for quit. Okay. What else? What else could cause a crash? Another common one would be to allocate, let's say, an array and try to go off the end of the array. And for arrays that are allocated on the stack, you have to go way off the end of the array. So we can try that here. We can do, let's say, int array, let's say with 10 elements. And let's go ahead and assign those elements. And then let's print them out. We'll compile the program, run it. It's going to crash right there. You can see it printed out a whole bunch of just garbage values. And let's try to figure out where it crashed. And it says here it crashed on line 9 of crash.c. Here's the line that it crashed on. So we can look back at our code and see line 9. This is the line that it crashed on. And if I wanted to kind of dig around a little bit and find out what was the value of I that caused it to crash, I could say print I. And it says it got up to 2,476. Now notice that our loop is going up to 10,000. So we only got about a quarter of the way through before it crashed. But again, this is not going to tell you exactly what went wrong, but it's at least going to tell you what line caused it. And then it allows you to focus your attention on the part of the program where the problem is likely to be. So the debugger is just a tool to give you clues about what might be going on, but it won't actually necessarily tell you exactly what's going on. Okay, so was that a useful piece of information for you about using GDB to find out where your program crashed? It's going to be more useful as we go on through the semester, because now that you have pointers, now that you have arrays, and pretty soon you're going to have memory allocation, these crashes are going to become more frequent. You're going to run off the ends of arrays. You're going to be dereferencing pointers that point off to nowhere. And your program's going to crash at that point. And you're going to want to know, where did it crash? What was my program doing at that time? Okay, so that was the first topic. So we just took our care of where did my program crash. And if you want a refresher on that, if you want some reference material on how to do that, if you go all the way to the bottom of our modules list, there is an item here that says, where is my program crashing? And it's got just a reminder about all the commands to use there. Okay, next topic is command line arguments. If you've taken the Linux or Unix class, or even if you just worked with the command line frequently enough, you know that when you type a command on the command line, oftentimes you don't just type a single word, but you might type more than one word. particularly when you're doing something like compiling. When you run the C compiler, that's a program out there. There's actually a program called Clang out there, and then you can supply some additional words that alter its behavior or supply additional information, like what's the C file that you want to compile, and any additional flags that you want to pass in, like the optimize flag or the debugging flag. So those all become what are called command line arguments. They're additional, they're almost like parameters to a function. You can think of Clang as being a function name, and everything you type after it as being parameters that you're passing into that function. So in this case, we've got 3 words on the command line. We've got the command itself, and then these 2 additional words over here. -G is a word, and crash.c is a word. And there can be, basically an infinite number of words on the command line. So when your program gets run, the shell that's interpreting your command will break up that command line into the individual words. It'll look for the spaces in between the words and then throw away those spaces, and leaving behind just the letters, put the words into an array. So inside of this array, this is array number, element number 0, this is element number 1, and this is element number 2. So this is going to make a 3-element array. The command itself goes into element number 0, and the remaining arguments go into 1 through n. So here's that example again. Clang-G. And we'll call this myprogram.c. And so it's going to make a 3-element array out of this. This is element 0, this is 1, and this is 2. And this array is going to be called argv, A-R-G-V. And there's another variable that gets created called argc, which contains the number 3 to let you know that there are 3 elements in this array. So you've got the array itself, and you've got the length of the array. So in order to use command line arguments, you have to declare your main a little bit differently. And if you're coming from a Java background, it's going to look a little familiar. Previously we just said int main and then 2 parentheses. But now you're going to write it like this. Int main int argc character pointer argv array. What is this? What is character star argv bracket bracket? So this says that we're declaring a variable called argv whose type is an array of character pointers. So this is basically an array of strings. It's an array of character pointers, and of course we know that character pointers are really just strings. And then argc is the length of the array. Now in Java, you know that we declared main usually to be, public static void main, and then string array args. But in Java, we don't have to have 2 separate variables for the length of the array and the array itself, because arrays in Java, you can find out how long they are with the length property. So it's a little bit different, but you'll recognize the things like arg here and array, and the fact that these are strings. So when you're using command line arguments, you just need to declare your main a little bit differently. Let's do an example of it. Oh, I hate leaf blowers. Do you hate leaf blowers too? Do you even have leaf blowers where you are? They're like an American scourge. of, can you, I actually, I don't even know, can you hear it? Can you hear the one that's my neighbor doing the leaf blower? You know, you may not be able to because the microphone is so directional. Oh, you can't hear it? Oh, thank goodness.
I turn the volume all the way up and listen hard. I can kind of hear a little
Oh,
noise in the
good.
back.
I'm glad that you can't hear it because they're so annoying. I don't know what it is about them that is so annoying. I think it's just that particular frequency that motor makes that I and millions of other people find really annoying. If they would just like change the motor inside these things from a cheap old lawnmower motor to something a little more like robust, you know, I think a lot of people would be happy.
I think they make electric ones now. They probably are not
Oh,
so
but
noisy.
the cheap electric ones also make this whine
Do
noise.
they?
Yeah,
No, I guess, yeah, just the wind turbulence.
it's that, and this is where I digress a little bit, right? Electric motors basically come in two varieties. There's brushed motors, which have an axle with two brushes that are sitting onto it, two or more brushes that are supplying the electrical power, and that basically the sound of those brushes going around and around and around create this noise because the brushes are actually making contact and not making contact. So they go on and off contact, which means they pass over little gaps in the commutator, and those gaps make a kind of a whining noise. Brush motors are cheap to make, and they're relatively powerful for the amount of size that they have. So brushed motors are in things like blenders, vacuum cleaners, you know, the old fans, like, you know, your house fans. You know, basically anything where you need a cheap motor that has a fair amount of power for the size, and you want it to be light and want it to be small. And then there are brushless motors, which don't have those brushes. They just use a whole series of electromagnets around the outside and a rotating commutator, and there's no actual contact between the magnets and the inside. It's all magnetic forces. And so brushless motors, also sometimes called induction motors, are a lot quieter. Those are the kinds that are in like your ceiling fans that make almost no noise whatsoever. And they're inside of computer fans, the fans that are on the back of your computer. Those are also brushless motors. And the only sound you can hear out of those is basically the sound of the air rushing through them, but you can't hear the motor itself. And then induction motors and brushless motors are also used in things like electric cars. That's why they can go so quietly. Their motors make almost no noise at all. But induction motors are much, much bigger and much, much heavier than brushed motors. So if the world would just use induction motors and take the hit on the size and the weight, the world would be a lot quieter. But you know, again, they're heavy, and they are large, and they're more expensive to make, and they're actually more powerful than brushed motors. They have a huge amount of torque, particularly at low speeds, but they're more expensive. So of course, no one uses them for small things. Oh, he's done. He's done blowing the leaves. Okay, so let's do an example of this command line argument. So we'll start off with our usual standard io.h, and now we're going to declare our main the way I showed you over here. And then let's just do something simple like loop through this array and just print out everything that we see. argc contains the length of the array. This is going to be used as our loop boundary condition. So we'll do a loop from 0, and we'll go up to, but not including argc, and then we'll increment I as we go. And then let's just print out the value of I and the string that we see there. And then that's our whole program. So if I just type in the name of the program without any command line arguments, it shows you that at the very least this array contains one element, element number 0, which contains the name of the command itself. So it literally just takes what I typed in as the name of the command, it puts that into this array. So it's not like the name of the program, it's actually what I typed in as the very first word. If I type in a complete path to this executable, that also goes there, right? So whatever I typed in as the first word goes into that array, basically untouched. But let's put some additional words after there. I don't know, names of foods. And we can see that this array contains 4 elements. Element number 1 is pizza, which is the second thing I typed in. Element number 2 is sushi. Element number 3 is chicken. Right? So it just takes the words that I typed in, breaks them up, looking for the spaces, and then what's left is just inserted right into that array. So as someone pointed out, this is essentially what the echo command is. If I type in echo, pizza, sushi, come on, I can't type today. All echo does is it just prints out all the elements that are in this array. So we can duplicate this behavior. So I'm going to make a program called echo, and the main is declared the same way. But now I'm not going to loop from 0 up to argc because I don't want to display the name of the command itself. So I'm going to start at 1. And then I'm not going to print out the number. I'm just going to print out the words. And instead of putting a new line after each line, I'm going to put just a space. And then when the loop is finished, then I'll put in my new line. Okay, and you can see that now my program behaves almost identically to, or pretty much identically to, the built-in echo command. Even if I type in some additional spaces in between each of the command line arguments, they get stripped out by the shell. And only the words themselves go into that array. So all the spaces that I type between them do not go into the array. Now, there's one additional thing that the echo command does, and that is if I pass in the -n flag to it, it behaves a little bit differently. In this case, it does not display that final new line character, and you get just the words that come out, and then the program ends at that point. So it doesn't go to the next line so that the prompt can be displayed on the next line. So the way you do that is you just write your program to look at the first command line argument, and if it literally is a -n, then you alter the behavior. So when you pass a flag into a program, the flags are not like a special thing that the shell does something with. It literally just passes in that word, a dash followed by an n, and then it's up to your program to figure out if that is an option. So let's write the program to do that. So the first thing we do before we get into this loop is we should figure out, is the first command line argument a -n? So if, and then we got to do some kind of string comparison here. I mean, literally what we're getting is a string that's a dash and an n. So how do we figure out if command line argument number 1 is a dash n? Well, we got to use our string compare function. So we'll look at element number 1, and if that is dash n. Now, have I told you about how string compare works?
Don't remember.
Yeah, I don't remember if I told you either. There's another one of those things like well, it was something that we really briefly covered last week.
Okay.
I listed out some of the standard string functions like string compare, string cat, string copy. Let me quickly go over them again. So you got string copy, string cat, string chr, this one here searches for a character within a string and tells you where it is. It gives you back a pointer to where that character is. And then string will search for a target string within a larger string. And then finally, string compare. You give it 2 strings and it tells you how those strings compare to each other. So string compare will return a 0 if equal. A negative number, let's call this string A and string B. If string A is less than string B, and it returns a positive number if string A is greater than string B. And by greater than or less than, I mean like if you were to like think about alphabetical order. So if I pass in pizza and sushi, then it would return a negative number because P comes before S, right? So the word pizza comes before the word sushi. But if I pass in 2 strings that are equal to each other, then I will get a 0 out of that. Basically, what it's telling you is what are the differences between these 2 strings. If there are no differences between the strings, you'll get back a 0. If there are some differences between the strings, you'll get back a non-zero number. So here we're going to say, are these 2 strings equal to each other? So if there are no differences between the 2 strings, then let's set a variable to indicate that we should not print a new line. Int, let's call this new line, and by default that'll be a 1. But if this first argument is a dash n, we'll set it to 0. And then down here we'll say if new line, print out a new line. I need to include string.h. So if I run my program and I just put in 2 command line arguments, it prints them out as usual. And then let's try it with dash n here. And well, it sort of worked, It did print out. It did not do the new line, but it also did the -n over here. I don't want to see that. So how do I fix my program?
I would make a variable for the beginning index and have it default to 1. And then inside that first if statement, set it to 2.
Ah, so if we're not printing out new lines, then we should start counting at 2.
Right.
But so we'll do int start equals 1. And if this is true, then start will be 2. Kind of like that?
Yeah, so that'll fix that. And then
okay. We end up with a little extra space here.
yeah.
That's another little if-else that you have to handle. But
And also what happens if you don't put any command line arguments?
oh, where did my program crash?
Well,
Yeah, how do we solve this problem?
you could do GDB.
Well, first I got to recompile it,
Oh, right.
and then let it crash. And what do you make of this report?
Well, it crashed in some system file.
Can you kind of figure out, well, yeah, definitely, it crashed in something that we didn't write. But can you kind of figure out what was the name of the function that it was crashing in? See, what happens is, oftentimes, there's these library functions like printf that we call. But printf is really just what's called a wrapper function. You call printf, and then what that one does is it figures out what's the real one I need to call. You know, there may be one that handles printing to the screen, and one that handles printing to a file, and one that handles maybe only printing out one single integer. Maybe that's more efficient to do a different way. So oftentimes, you may call a function, but another one actually gets called. So which one do you think this refers to?
Well, probably string comp.
Probably string compare.
But we can do backtrace, right, to
Yep.
see.
And it says here that line 8 of echo.c is where the program crashed. So that's this one here. So what could be going on? Do we have enough information to be able to figure out what's happening?
I think so, because so that line says argc is 1. So that means the array length is 1, which means the only valid index is 0.
Ah, so we're trying to look at element number 1 of this array, but there isn't an element number 1. So we've fallen off the end of the array. So that means that we can't even look at the first command line argument if there isn't one to begin with. So we're going to have to put another check up front to ask how many command line arguments are there, and if there aren't any, we'll just end the program at that point. So if argc is equal to 1, so if there's only one element in the array, and there will never be 0 elements in the array, there's always going to be at least 1. If argc equals 1, then we're done. Let's just return. Oh, it's a return a value, so let's return a 0. Oops. compile program, we'll run it, and then, so without any command line arguments, we get no output at all. And then with, you know, at least one, we got that. And then let's put in our -n, and that seems to work. And the last thing to do is, what happens if we put in -n, but no other command line arguments? Well, I guess it seemed to work. Let's see what echo -n with no command line arguments does. It seems to behave the same way. So I think we have a reasonable facsimile here of the echo command. So what did we learn from this? We learned, first of all, that what you should do, a good practice is check the value of argc right up front. Do that as the very first thing, and make sure you've got enough command line arguments, or at least you're handling the behavior if there aren't any at all. So I would put right up front a check on argc to make sure, like if you are writing a program and the user has to give you 2 command line arguments, you should check to make sure that you've got at least 2 or exactly 2. Do that right up front before you do anything else. And then you can check for these flags. And if you see a flag that you're interested in, you can set a variable to indicate that you saw that flag. And then you can loop through the remaining arguments, or you can access them individually like you would any other array. And you can see how the presence of that flag that we had set changes the behavior of the program later on. Okay, and the last thing is the array, the argv array, will always contain at least one element. It'll never contain none. So when you're checking the length of the array, the minimum length is going to be a 1. It'll never be a 0. At least I can't think of any situations where it would be 0. All right. So did we take care of command line arguments? So next thing is memory allocation. And I'm just going to briefly cover this. There's not a whole lot to say at this point, except to kind of like show you that it exists and show you that we can use it. And the reason why I wanted to bring it up is because in that CSI assignment, it gets used in there. When the program needs to create that large array of the bytes from that file, it doesn't know ahead of time how many bytes that array should be. And also, that array gets created in the read card function and gets passed back to the caller. And if you try to create an array inside of a function, you can't pass it back because that array is a local variable to that function and it will disappear once the function is done. So that program uses a memory allocation, a dynamic memory allocation, in order to set aside memory for that array, and then it's able to pass that back. And that array will persist until the program ends or until the programmer frees up that memory. So in order to use this memory allocation, you need to include the standard library and then that gives you 2 functions, one called Malloc, M-A-L-L-O-C, stands for memory allocation, and it gives you another one called free. So one is used to allocate memory and one is used to deallocate the memory. So with Malloc, you pass it, well, you just pass it one thing. You just pass it the number of bytes that you want to set aside. So when you call malloc, you're just going to tell the operating system, I want you to set aside this number of bytes. And then the operating system will go and reserve that chunk of memory to you and then pass back to you a pointer to that chunk of memory. So for example, if I want to set aside 50 characters for a string, I would do malloc 50 and then assign that to a character pointer. So this will set aside a 50-byte array. And then you'll create a variable called s that'll point to that. And then you can fill it up as you would any other string. I'm going to just move this down. What if I want 100 integers? So I can't just say malloc 100 because that would set aside 100 bytes. I don't want 100 bytes because that won't be big enough to hold 100 integers. How many do I need?
For 400, right?
I need 400 because each int is, at least on our system, is a 32-bit quantity. So a more typical way to do this in C is have the program do the calculation for you. So this is a kind of an idiomatic way that you'll see programmers figure out how many bytes to actually set aside. The first thing you'll put in is how many boxes you want, and then you will multiply that by the size of each box. So this is going to ask for 100 boxes multiplied by the size of each box. And in our system, this will return a 4. So then it will multiply these two together. It gets you 400. And then we can assign that to an integer pointer. Okay, it's pretty easy to do. So this is the more traditional way that you'll see it. The number of elements you want multiplied by the size of each element, and then you're going to assign it to a pointer to that kind of thing. You'll notice that the int here and the int here are the same. So you'll want to make these match up here. Okay, you're not going to put int pointer here because we're not storing an array of pointers. We're only storing an array of integers. So just put int here. When you do your declaration, you're going to put the same type here and then a star and then the name of the variable. So that's kind of a recipe to follow, is that this type here and this type here should match. Okay, so finally, how would I allocate 25 bloops?
Malloc 25 times size of bloop.
malloc 25 times size of bloop. And then what do I assign it to? Over here on the left side.
A bloop pointer.
Good. A bloop pointer. Let's call it B. So B will point to an array of 25 bloops. Like that. Okay, so that's all malloc does, is it just sets aside the memory that you ask for and then returns a pointer to it. And you know, a good programmer would check to make sure that malloc actually worked. So if you get back a null pointer, then you know that memory allocation did not work. And yeah, so I'm always kind of like a little on the fence about should you check the result of every single malloc, or is that extra work that is getting in the way of getting your assignment done? Because on today's systems, it's not likely that malloc is going to fail, at least for the programs that we're going to write. On a constrained system, maybe one of those little like Raspberry Pi systems or a little microcontroller, sure, a malloc might fail because they just don't have very much memory at all. And you probably would want to check to see if the memory allocation worked. But on our systems, it's not likely to fail. So I would say if, you know, in a real production system, yeah, you would check every single time you did a malloc. But on ours, I'd say don't worry about it. I mean, it's the extra work, and what you're really worried about at this point is getting the data structure right. What's a bloop? I don't know, I just made it up. But I wanted to use something nonsensical so that you would see how this recipe is constructed. Okay, and then whenever you allocate memory, it'll stick around until your program ends, at which time the operating system will reclaim it, or until you explicitly release it for reuse. So all you do is you call free, and then pass it in that pointer that points to the beginning of that, chunk of memory. And then it'll just release it. And it's possible that that memory will get recycled and reused the next time you call malloc. And that's why we always say that when you allocate a variable, it contains like junky values, because if it recycles a block of memory, it's not going to clear it out. It's not going to fill it with all zeros. It's just going to simply set aside that chunk of memory and then hand you back a pointer to it. And whatever happens to be in that memory is what's there. So let's just do a quick little example here. Let's have a function. Let's not do that yet. Let's just show an example of using malloc, and then we'll fill it up with some values. Let's do something like, let's prompt the user to have them tell us how many numbers they're going to type in so that we can do the malloc correctly. So let's go int, let's call it how many. Okay, now we're going to use malloc to create the array. So I want to create an array of this unknown number of integers. I don't know ahead of time how many it's going to be. So we'll go int pointer nums equals malloc, how many, times the size of an int. And then we'll just fill it up. Let's see, we'll do a loop. Actually, I'm not going to prompt the user. I'm just going to have it fill the array with like multiples of 100 or something like that. And then we'll print it out. That should do it. Let's compile this. What did I call it? Malloc. Let's do 5 numbers, and then it filled it up with 0, 100, 200, 300, and 400. So looks good. And then if I run it again, and I do 10 numbers, then I get an array that can hold 10 numbers. Okay, so here's that malloc up here. This is how many we want to put times the size of an integer. And then malloc will return to us a pointer to that chunk of memory, which we can treat just like an array. And then we can fill the array, we can access the array. Now when our program ends, the operating system will reclaim that chunk of memory, but it is a good practice as a programmer to deallocate any memory that you set aside using malloc. And basically for every malloc, there should be a free, so that they're kind of symmetric in your program. So when you're done with that chunk of memory, you should call free and then pass in the pointer to that chunk of memory. And the behavior of the program is identical, but now we are cleaning up after ourselves to make sure that all the memory has been deallocated. What happens if, let's see, there was a question here. What's going to happen if we don't mention about how many and we get a single 32-bit chunk? So if we do a malloc and we don't multiply this by how many. And then with pointer arithmetic, keep adding the chunks. Do you mean like doing an additional malloc, or do you mean like going off the end of the array? That's where I'm not understanding your question. Do you mean like keep doing more mallocs, or go off the end of the array? And like, so basically just compile and run the program as it is right now. Let's go ahead and try that. Let's just run it. And well, it seemed to work, right? Even though we only asked for one integer, it was actually able to store all 10 of them. And you're saying with point, now I'm looking here at the comment. So right here, if we do star nums plus 1 like that, remember that when we use this pointer arithmetic and the star in front, and then a plus, and then an index, that's like exactly the same as using the angle bracket, the square brackets. Right, just a reminder. But if I do nums bracket 2, that is the same as star nums plus 2. So writing it in this style using pointer arithmetic and writing it using the brackets are completely identical. There's no difference to the compiler, and there's no difference to the assembly code that gets generated. So whether I do it like this or with the brackets, they're absolutely identical. But let's try it the other way regardless. So you can see it behaves exactly the same. So what's going on here? Why did this work? So did this actually allocate an array with 10 elements in it? And the answer is no. It created an array with 1 element in it, but you're basically walking off the end of the array. The memory is there, but you're just going off the end of it. Remember when we were declaring local arrays? We were able to walk off the end of the array by a certain amount before the program would crash. And the same thing's happening here. Although we asked the operating system to set aside space for only one integer, there's actually some excess space. Because what happens underneath the hood is doing a malloc is actually computationally expensive. And when we say expensive, we don't mean like actual dollars and cents, but we mean like what's the amount of work that has to be done in order to set aside this chunk of memory. And a fair amount of work has to be done. There's some what we call bookkeeping that needs to be done to keep track of where these chunks of memory start and end, and do we have space to fit this chunk of memory in. So what actually happens behind the scenes is when you call malloc the first time, it will then turn that into a memory request to the operating system. When you call malloc, you're not actually interacting with the operating system. You're interacting with a library of code that gets attached into with your program. It's part of the standard C library. So when you call malloc, it doesn't actually ask the operating system for a chunk just the size that you asked for. It actually asks for a larger chunk. So you may call malloc and ask for 10 bytes, but then malloc will turn around and ask the operating system, let's say, for a kilobyte, 1,000 bytes. And now it'll reserve 10 bytes for your call to malloc with 990 left over. And then the next time it calls malloc, it doesn't have to go and ask the operating system for an additional chunk of memory. It's already got this larger pool of memory that it can pull from. And then let's say your next malloc is for 40 bytes. It just simply sets aside the next 40 bytes out of this chunk that it asked for. And there's no need to go in and invoke, and you get the operating system involved in this, because the operating system is busy. It's a program that's managing all the resources of the computer and all the competing processes that are running on the system, asking for memory, asking for network, asking for files, right? Operating system is just so tired doing all that stuff. No, it doesn't really get tired, but it's just got a lot of work to do. And so when a program needs to ask for a chunk of memory, it's kind of like got to stop what it's doing and go and find a chunk of memory to give to it and then hand it back to your program. And so the standard C library would rather ask the operating system for a larger chunk of memory and then slice that up as needed. And only when that initial chunk fills up, then it will go and ask for another chunk of memory from the operating system. So the fact that we were able to go off the end of the array means that it asked for a larger chunk of memory. The memory allocator library only set aside space for one element, but there was plenty of space left over, and we were able to run off the end of the array. Now, if we were to then call malloc again and create another array, it's quite likely that that new one will follow the one that we had just set aside and run off the end of, and then we would probably overwrite some memory. In fact, we could probably try that. Let's go ahead and we'll fill the array here, and then we will allocate another array. So let's go int pointer, let's call it nums2 equals malloc. Size, let's do, I don't know, let's do, I don't know, let's do like 5 elements there. And then we'll fill it. With some different numbers, let's say multiples of 3, so that we'll be able to identify them pretty easily. And then we'll display that nums array. See what happens.
You have a typo in the variable name on line 20.
Thank you. Ha! All right, so it turns out it didn't work. So let's see, what happened here? So we allocated an array with only one element in it, so really just 4 bytes. And then we walked off the end of it here. And then we allocated another array, and it says that the malloc failed. So it's actually this call right here. We can make sure that that's actually what happened. And then it's line 20 here. This malloc failed, presumably because when it sets aside a chunk of memory, and I'm just speculating here, but if I was the person who wrote this library, I would set aside a chunk of memory, and then I might actually put a little marker at the end of it to say this is the end of that chunk of memory. So when I go and search for another chunk of memory to allocate, I can go and find that marker, kind of like those delimiters within a JPEG file, right? I can basically scan forward, find that marker, and then I know that the next chunk of memory can follow that. And so what I think has happened here is that when we ran off the end of that chunk of memory, we overwrote that special marker that it was looking for. So when we called malloc a second time, and it goes and it scans for that mark, it goes, whoa, I don't see that here. So I'm going to throw an error and say something got messed up in my memory allocation, and then it just crashes at that point. So yeah, if you only do one malloc, you can run off the end of the memory, but if you do more than one malloc, then you really shouldn't be running off the end because you're now going to be stomping all over other arrays. And that's probably a bad thing to do.
What happens if you move that malloc before you fill the first array?
So let's pull this out. Just allocate both arrays all at once. Kind of like that.
Yeah.
Well, then it worked. No crash. Because it allocated the first chunk, and it set aside those bytes, and then it allocated another chunk, and everything looks good so far. It finds those marker values. And then we go and write our program that starts overwriting the arrays. But malloc has done its job. It's finished at that point. But we can see also here that here's how far it got through the array before that next one took over, right? So it didn't actually start here, but started a little bit later, which means there's not only just like one marker, there's actually several bytes worth of markers that it's setting aside. And then the one last thing I want to try is we also need to free up nums2, and I'm wondering if that will have a problem. Yep. That one crashed because now when you free up nums2, it's again looking for those markers and it doesn't see them, so it knows that the memory got corrupted somehow, and it just kills it at that point. So not a good idea to go running off the ends of your arrays, particularly when you're using Malloc, because as a result of doing its housekeeping and bookkeeping, it's put in these additional pieces of information in amongst the chunks of memory. And if you go off the ends of your arrays, you're going to be overwriting that stuff. There is actually a third function, which we will talk about in a week or two, that has to do with memory allocation, and that's one called Reallocate. That's used to change the size of a chunk that's been allocated. See, with standard arrays, once you create an array, you can't change the size. You can't make it longer, you can't make it shorter. But with this dynamic memory, you can make it longer. You can call reallocate, and then it will resize your array. It'll make it either longer or shorter. And so this gives you something that is very similar to the array list in Java, which can grow and shrink as necessary. So in C, there's a function called reallocate that can be used to change the size of an array. And it's actually pretty cool. It's actually a little bit better than the array list inside of Java. The array list in Java always incorporates some kind of performance penalty, where reallocate can actually work a little bit faster than the array list can. Okay, well, so that's just a quick thing about Malloc. We'll be using Malloc more as the semester progresses. In fact, almost every program we write from here on out is probably going to use Malloc. Can we implement the generic array in C? Like, can we basically do an array list? Yeah, you can. I mean, once you have Malloc and reallocate and free, then you can implement essentially array list. What you don't get with C is any kind of templating or generics, right? You can't pass in like the type of something inside the angle brackets like you can in Java or C++. But you can sort of simulate it, sort of. By doing things like passing in the size of the thing that you want to store in there, and then do some fancy stuff with memory copy and casting and things like that. So it can be done, and it has to be able to be done because C++ is the compiler itself. Its underpinnings is just C. So whatever C++ can do, C can do as well, maybe just with a little extra work. You can do it. It's just kind of messy. All right, so where are we on our list of things to do? So we're right here at memory allocation. So I think what I want to do is, it's 10:50 now, and we didn't really get to files. So if you want to hang around, we'll take a short little break, maybe 10 minutes or so, and then when we come back, we will go over the assignments that I didn't get a chance to go over. So there's a couple of warm-ups and there's a level up, I think, for us to do. And then I can very briefly introduce files, and then we can look at those assignments. So there's kind of like we've kind of like got some assignments that have been kind of stacking up, and we'll take a look at those. So let's take a short little break, about 10 minutes or so, and then we'll come back and we'll take a look at those.
Recording stopped.
All right, that's the Zoom recording that has stopped. But as far as YouTube, it keeps going. So let's see if we can address some of the questions that came up. For doing core dumps. So on an Ubuntu system, by default, you will not get core files. Core files can be fairly large. If your program is consuming lots of memory, then if it crashes and it creates that core file, it creates a snapshot of your computer's memory or the program's memory when it crashed. And if your program was using 10 or 20 megabytes of memory because you're creating huge data structures, then you get a core file that is 10 or 20 megabytes. And those things can stack up after a while. Some systems will come with a periodic program that kind of sweeps through, let's say, once a day or once a week and finds these old core files and just deletes them because they can consume space. And also on an Ubuntu system, by default, if you do tell it to allow core files to be generated, they don't go in your current directory. They go off into a system directory. And why they chose to do this, I'm not entirely sure. I think it might be because, yeah, and actually, you know, if I was in that position of designing a system that if a program crashed, it would generate a core file but not show it to the user, I'd probably do that, because if your goal of an operating system is to be something that the average user can use, run a web browser, run a word processor, play a few simple games, then if a program crashes, you probably don't want them to see these core files. They're just like mysterious files and you don't know what to do with them. And then the user's probably left wondering, should I delete this? Is it okay to delete this? Where did this come from? I don't know what this is. So the default behavior on an Ubuntu system, at least, is don't generate core files. And if you do generate core files, put them off in a system directory where they're not normally seen. And so you as a programmer might want to alter that behavior. And so there's two things you need to do to get it to drop these core files. Now in our development system here, I've made those two changes, and so you get these core files by default. So the first thing you need to do is share your screen. So you need to tell the shell to allow core files, and you type ulimit -c unlimited. So ulimit is a command that sets up some default settings in your environment, your user limits, and it can do things like set the amount of memory that a process can use, and it can set the amount of time a process can take up. So if a program exceeds those limits, it's automatically just terminated at that point. -c tells it to change the limit on how big core files are, and by default the limit is 0, and a limit of 0 means core files never get generated. So we're setting it to unlimited to tell it we can create core files of any size. So this is done on a per session basis. The next time you log in, you'll have to run this command again. If you want to make it permanent, you can put it into your .bashrc or .bash profile down at the bottom, and then the next time you log in, that command will get run, and then you'll be able to create core files. And the other thing you have to do is you have to change where it saves those core files. And the default is off in some system directory, and you need to change that. And now I don't remember how that is done, so let me go and Google that. Here it is. It is in this file, proc sys kernel core pattern, and you have to be the root user in order to change this file. Proc sys kernel core pattern. And what you would normally see there is a long string showing you the name of the directory where this core file is kept. Let me see if there's an example of it here. So yeah, normally it looks like this. Yeah, it looks something like this, where it's going to put in core and then dot and then I think %p, which is the process number. So every time your program crashes, you get a brand new core file with a number tacked onto the end, which also leads to this core bloat that you see on the system, where every time a program crashes, it creates a brand new core file and doesn't overwrite the previous one. And so I've gone in and I've changed this core pattern to be /core, which means just put the core file in the current directory. Don't put any suffix on it, so that the next time your program crashes, it just overwrites the previous one, which is the behavior I want. So 2 things you need to do. You need to set it to unlimited core file sizes, and then you need to change this core pattern. And again, if you Google around, how do I change the location of a core dump, it'll give you like a command that you can type in that will just change it. Once you set this one, once you set the location of the core files, that's permanent, I think, until either the system is rebooted or you run updates that goes and changes that file back. So you might need to go and periodically so if you run a program, it crashes, and then you don't see the core file there, then go and look in this directory, or go and look in the directory where it was writing to and see if the core files are appearing there. And if they are, you know that something has gone and changed this core pattern back to what it was. A system update or a reboot, I think, will change it back. Next question, where can you see the returned value from main? Ah, that's a good question. So you can see it in the shell if you echo $? So there's a variable called question mark. That's the actual variable name. And it shows you the return value from the previous command. So if I write a program, let's see, here's our echo program right here. And let's say I set this to return 1. Now I need to compile my program again. So remember, if there were no command line arguments other than the file name itself, the command name itself, then it's going to return a 1. And so if I echo $? There's that 1 right there. And then if I run the command, with at least one command line argument, in which case it'll fall all the way to the end and do an implicit return 0, then echoing $? will show you that 0. If I was writing a shell script where I'm running commands, I might want that shell script to be able to know whether a command succeeded or failed. One example might be, let's say I'm prompting the user to enter something to search for, and then I use the grep command to search for that thing. So grep will return one of 3 values. It'll return a 0 if it found that thing that you're searching for. It'll return a 1 if it didn't find the thing you were searching for, and it'll return a 2 if you misconstructed the command itself. Like you passed through flags it doesn't understand, or the pattern you're searching for is not a valid regular expression, then it'll return a 2 to you. So it'll return a 0 if it found what it's looking for, a 1 if it did not find it, and a 2 if it was an invalid command. And so your shell script could then look at that return value and determine what to do. Like if it didn't find the thing it was searching for, you could display a message that says, didn't find it. So that's your shell script could then use this variable to alter its behavior depending upon whether the previous command worked or not. Remember, 0 typically means the command worked, and then anything other than a 0 means it didn't work. And where you can find documentation on those return values is, let's see, grep manual. Pretty much for any command. If you go all the way to the bottom, usually there's a section called return value or exit value. And here would be an
I saw
example.
exit values go flying by there.
It did, where was it? Copyright, bugs, example. See also, was it further up?
Yeah, it was up higher.
I passed it. Usually it's, oh, here it is, exit status. Thank you. Exit status is 0 if the line is found, 1 if no line was found, and 2 if an error occurred. So grep has 3 possible ways it could return. There are some commands that have like dozens, and every single one of those status codes means something. Any other way of parsing command line arguments? Yeah, there's some standard library. I think there's one called standard arg. Oh, no, sorry. Standard arg is for handling variable arguments to a function. That's not what we want. Oh yeah, get opt. That's what I'm looking for. So you could use, yeah, get opt. Handles simple argument parsing tasks. Basically, if I recall, the way you use get opt is you pass it flags that you are looking for. You know, this one here is looking for either a -I, a -L, or a -W. And then you can, it'll return to you, you know, a little flag, a number basically, and then you can use a switch statement to figure out what options actually got passed in. And then you can set your variables based upon that. So this get opt will handle things like any command line argument that starts with a dash will get caught by or flagged by get opt, and then it will allow you to set variables based upon what it saw. And then it will also display an error message if you pass in a flag that it's not expecting. So if I pass in like a -Z here, then it will fall down to the default case and you can print out an error message of some sort. And then there's another one called argp, which is, I think, like a little more sophisticated. It allows things like simple command line arguments, like with single characters. It probably allows like dash command line arguments, the ones that start with 2 dashes. And then there's also an example here of doing it all yourself, which is essentially what we were doing, right? We're just doing string compares. Get arg. It's part of the Fortran library. I think pretty much get opt is the one you're normally going to use. This one.
Recording in progress.
All right, we're back. Let's take a look at the assignments from this week and last week. Where were we here? Pointers, input, we did that. We did that. Here we go. So there's a warm-up here called string functions. And this one uses the standard string functions: string copy, string cat, string compare, string string, string character, and fgets. And the way this program works is, again, this is a warm-up, so it's not really designed to be something terribly useful. It's just to get you used to using these string functions. And basically the idea is it's going to repeatedly prompt you to type in a string, and then it's going to take that input and use it to build up a longer string. And you're going to keep doing this until the user types in the word done, at which case you'll print out that longer string that you've built up. So it's going to take the short string the user inputted and decide where to place it in the longer string. And you got two choices. You can either place it at the beginning or at the end. You're never going to put it in the middle. You're always going to put it at the beginning or at the end. So the first time you type in a word, it just puts it into the longer string. The second time you type into a word, it figures out where it goes. And it's just going to do a simple string comparison here. You're just going to compare the input the user typed in against the longer string. And if the input goes in front, it just goes in front. And if it goes behind, it goes behind. So here we can see the first string was hello. The second string was world. So obviously that goes after hello. So it goes on the end. Then we type in bye. And obviously bye goes in front of hello world, so it goes up here at the front. And now we type in cat. Okay, now cat comes after bye hello world. Alphabetically, cat comes after bye hello world. So it's going to go on the end. Doesn't go in the middle, it goes on the end. Okay, and then the user types in WORL. Now, WORL is contained within the string, it's contained within world, and so we're not going to do anything. We're just going to leave that one. And then beep. Beep comes before bye hello world cat, so it goes up in the front. Bingo comes after beep bye hello world cat, so it goes on the end. Right, that's all it does. Right, just string compares. You're not trying to sort the words. You're not trying to insert anything in any special order. You're not trying to reverse them or anything like that. They either go at the beginning or at the end. And when your program and when the user types in the word done. So that's all you're going to do for that program. Use things like fgets to get input. You want to strip off the new lines. Use string character to locate the new line. Use string to perform searches. Use string compare to find out whether it goes at the beginning or the end. You're going to put this into a repository called Lab7. You'll add it, commit it, and then you can push it at this point, but you're also going to put one other program into this repository. So you're going to do the other warm-up assignment into the repository as well. Okay, so that's that program there. And the next one is command line arguments. So this is going to work just like the one we just did, except that the user is going to type in the words on the command line. And then it's going to display the strings as it builds them up. There's no need to put the word done on here because we know where the command line ends. Otherwise, it works the same way. So you'll put this into the repository, you'll commit it and push it, and then make sure to add me to the repository so I can see it, and then you just turn in the URL to the repository, and then I can go and fetch it from there. So that's the assignment for that one. And then finally, if we got some time, probably we do, we can look at this assignment here, display matching lines. This will be a warm-up. We're not going to talk about this hashing one. We'll do that next time. So let's just do this warm-up right here, 8.1. Actually, now I'm wondering, because I'm looking at the due date on this, October 26th, right? That's like 2 weeks from now. What that means is that in our schedule here, we're not actually supposed to be doing this until next week. So I don't know. I think what I'll do is I'll just briefly introduce files to you since we have some time, and then I'll let you look at those assignments there on your own time. So I'll briefly introduce files, and then we'll talk more about them next week. So I hope you're already kind of familiar with what a file is. Now, if you're coming from a computing environment where you never have to deal with files, like the only computer you've ever used is your phone. But, those phones hide files from you. All you see is things like apps and games and contact lists and text messages, and you may not realize that behind the scenes, all those things just come from different files on your computer. And a file is basically just an array of bytes. With a couple of differences. The first thing you have to realize about this array of bytes is that it doesn't really have random access. You can't look at element number 1 and then go and look at element number 100 without a fair amount of work, right? So this is a linear data structure. You start at the beginning and you can go towards the end, but you can't just jump around. I mean, you can with a file. It's really slow to do that. So you want to access a file from beginning to end. There's 4 basic operations you can do to a file. You can open it, which means, get it ready, make it available to your program. You can read from it, you can write to it, and you can close it. Closing means to basically, remove access from your program to that file, and also make sure that any bytes that need to be written out to that file have been pushed out to disk. So the function to do open is fopen. The function for read are just the functions you've already been using, just with an F in front of them. So we got things like fgets, fscanf, for writing to a file. You can use things like fprintf. And then for closing a file, it's called fclose. There's 2 more reading and writing functions. There's fread and fwrite. We're not going to need these 2 until later in the semester. So right now you just need fopen, fgets or fscanf, fprintf, and fclose. Those are the ones you need. Actually, what am I going to do here? I guess I'll underline them. This one, this one, this one, this one, and this one. All right, fopen. You pass it 2 parameters. You pass it the file name, the file that you want to open, and then something called the mode. And the mode is going to be, and there's actually many different modes you can put here, but we're only interested really in 3 of them. The string R, the string W, or the string A. R stands for read, W stands for write, and A stands for append. Okay. So, and then fopen will return to you a file pointer. This is one of the few places in C where a variable type is going to be all capitalized. And I don't know why they chose to do this, but that's the way it is. It's one of the only types that is all capitalized, but it does stand out. So we could do something like this. File pointer, let's call it out. And then we say out equals fopen, the name of the file that we want to write to. Let's say we'll call it greeting.txt. And file names on Linux systems don't have to have an extension, but if we put them there, then we know what they are. We know what kind of things they are. And then we're going to do this for writing. Then we could do something like fprintf out, and then the string we want to put there. So fprintf is just like good old printf, except it's got one additional parameter, and that's the file that we want to write to. Not the file name, but rather the variable that we got back from fopen. And then when we're all done, we're going to go fclose, and the file pointer that we are writing to. So quick program. We'll go file pointer out equals fopen greeting.txt, and we'll open it for writing. And then we will use fprintf to write the string hello to it, and then we'll close it. Let me save that, and we'll compile it and run it. And nothing will appear on the screen, but we do have a new file over here called greeting.txt. And if we look at it, it contains the string that we put in that file. That's it. This is all you really need to know about files. Oh, let's do a couple more things. Let's change this greeting to, bonjour. And then I will compile it and run it. And what's going to happen? What's going to happen to this greeting file? What's it going to look like?
It's just going to have the word bonjour.
Yeah. So the contents that were there have been overwritten with this new contents. When you open a file for writing, if that file already exists, it will erase the contents of that file and replace it with new contents. And it will not prompt you, it will not say, are you sure? It will just simply overwrite the contents of that file. So if the file does not exist, the file will be overwritten. If the file does exist, then the file will be overwritten. If it doesn't exist, then the file will be created, as you would expect. So be very careful with the write mode, and just be aware that it will overwrite. Usually that's what you want to do. You're running a program, you're generating some output, you're going to want it to overwrite the previous stuff. But if you wanted to keep it, it's not going to ask you, are you sure you want to throw this away? The A mode over here is used to append, and in that case, it's just like write, but it'll retain the original contents and start adding new contents to the end of the old one. That's what append means. Stick it onto the end. So it's going to retain the old contents. It won't overwrite it, and it will start adding it on to the end. And we'll go over next time a little bit more about file internals and discuss exactly what's happening when we do things like read and write and append. And then finally, if you use read, it will open the file for reading, and then the contents of the file will not be disturbed. It'll leave them the same. Okay, so if we change this to A, and then we compile the program and run it a few more times, then it just starts writing bonjour every time we run the program. So it goes on to the end of the file. Okay, let's write a quick example of reading from a file. Let's pick a file here that we want to read from. And it can be actually pretty much any one of these files that's just a text file. So, I mean, we could read from a JPEG, but it's not that interesting to display the stuff in there. Let's, what do we have here? Well, there is this file called welcome.md, which is a welcome message that, we normally don't see because we don't start well. You would see this file if you opened up your environment and you had nothing else to display. But actually, let's open up this file for reading, and we'll just display it on the screen. So let's open up welcome.md for reading. And then something I need to point out is you need to check the return value from fopen to make sure that it actually opened your file. There could be one of many reasons why it might not open your file. So the way you check is to see the return value. You look at the return value, and if you get a null back, then you know that the file wasn't opened. Null is all in capital letters in C. So if we couldn't open the file, what should we do? We can't obviously proceed with the rest of the program because the file's not open, and the whole rest of the program is to deal with a file that's been opened. So at this point, we might just want to exit the program. We might just say there's nothing else we can do. Maybe we can reprompt the user or something like that, but we're not prompting the user in this case. We're just trying to open the file that we named right here on the fopen. So at this point, all we can really do is just exit. Now, normally I've shown you how to use return, but return only works if you're inside of main. Then you can return out of main and you're done with your program. But if you're anywhere else in your program, you just want to end it at that point, you have to use exit. And you have to pass in that status code. In this case, I'm passing in a 1 to indicate that something went wrong. Right? 0 means everything was great, but 1 means something was wrong. So to use the exit, you're going to have to include standard library. There's a lot of stuff that comes with standard library. Memory allocation, memory deallocation, and then this exit comes with it. Also things like, what was it, the random function I think was also in there. So there's quite a bit of stuff in this one here. All right, so now that the file is open, we can start reading from it. Now, we don't know how many lines are in that file, so we need some kind of loop that's going to end when we reach the end of the file. So there's a couple of ways to do this. There is a function called FEOF, or detecting if the end of the file has been reached. Let's look at that. FEOF. So it tests the end of file indicator for the given file, and it'll return an integer to you. And it'll return returns a non-zero value when the end of file indicator is set. Otherwise, it returns a 0. So basically, it tells you if you have reached the end of the file. So we want some kind of loop. We'll go while FEOF of the input is not equal to 0. So if we haven't reached the end of the file, then it's okay to go ahead and get some input from it. Let's see, since we're dealing with a file that contains a bunch of strings, let's use fgets. We need to pass in 3 things. The string that can, and now remember, fgets only reads in one single line, so we're not going to get the whole file. We're just going to get one line out of the file. And we need to also set aside an array for that. So let's go character, let's call it line, and let's give it a total of 100, right? Because I'm pretty sure that nothing in here is longer than 100 lines, 100 characters. Oh, maybe something is. I don't know how long this is. Goes up to 89. So 100 should be good enough. But this is one of those cases where you kind of have to be careful, because what if it's longer? Okay, so if we're not reached the end of the file, let's call fgets. We'll pass in the line 100, and then we're getting input not from standard input, but from in our file. And then let's go ahead and just print it out. And then when we're all done, we'll close it. And when, oh, nothing happened. I did not expect that. So let's see, what could have gone wrong? So we opened the file, and then we check to see if this is the end of the file, and if it's, let me just make sure f in a file returns non-zero when the end of file indicator is associated, otherwise it returns 0. So that seems to be okay. Anybody else know what's going on?
Don't you want that test, wait, to be equal 0? Isn't it non-zero when it does find the end of the file?
Right.
So
oh,
it's
yeah.
0.
So this should be equal to 0, right?
Right, I think.
Well. Oh, yeah, that was it. So if we look at the original file over here, this is what it looked like. Now, this came out all double-spaced. Why is that?
So I guess fgets includes the
Right, just like
new line?
we've been used to. fgets includes that new line. So there's a couple things we can do. We can just simply not print out an extra new line. Or we could go and strip it off and then add it back. There, that looks better. Now, you might be thinking, like, this one looks like it's in colors, right? There's like a purple color here, and there's purple here, and this is in bold. How come when I print it out, it's not in color, it's just in black and white? And the answer there is, it's not really in color to begin with. This is just a text file. Text contains nothing but just characters. Anything about character formatting, like colors and bold and things like that, are not in the file itself. What's making them bold and colored is not the text file, but my editor. My editor recognizes that this is what's called a markdown file, and then highlights things that are headlines and puts things in colors to make them kind of stand out. So this coloring that you see is not in the file. Same thing's going on with things like my C files. The pink and the orange and the blue is not in the file. It's just my editor highlighting things in different colors to make them easier for me to see. So when we run our program and we print it out, you're not going to see any of those colors. It's just going to be black and white. Okay, so the thing there is that just like with, any other use of fgets, it's going to put the new lines on the end, and if you want those new lines to be stripped off, you're going to have to do that yourself. All right. So I think that's enough of an introduction for files to be able to, at least get started with that matching, printout matching lines assignment. And basically there, you're just going to be kind of simulating what grep does, except without all the fancy pattern matching. You're just going to open a file for reading. I think you're going to get the file name off the command line, as well as the thing to search for. And then it's just going to display any line that it finds that has that substring in it. So it's going to be kind of like grep. You pass in the thing you're searching for and the file name to search through, and then it opens that file for reading, reads it in one line at a time, and then displays the lines as it goes. Now here's something that I see a fair number of students that come from a Java background doing in their programs. And I can understand why you would do this. That in a command line driven environment like what we're using, it's perfectly okay to open a file for reading and then read in one line of the file and then do something to that one line. In this case, maybe it's, display the matching lines. So you read in that one line of the file and determine if that line matches or not. If it does match, you just print it out and then move on to the next line. And then determine if that one matches or not, and if it does, just print it out and move on to the next line. So you're processing your input file one line at a time and printing out your results as you go. And you're going to essentially retain a history of all those results in your terminal that you can scroll up and down and look at the output from. So it's a kind of a different style of programming, of processing a file one line at a time, doing something to that line, and then moving on to the next line. The advantage of this is that once you're done with that line, you don't have to keep any information about it, unless you want to, right? You don't have to store stuff away. What I see some students doing who are coming, I think, from a Java background is, since Java, the way you use Java is not normally in a command line terminal style, but more like graphical stuff, is there's a tendency to want to store away all the results in some kind of an array. And then when your program is all done processing the input file, then run a little loop to display the contents of that array. And that works, but you don't need to for these kinds of programs, because you can just simply output your line as you processed it and then move on to the next line. And you can scroll up and down in the terminal to see everything that you've done. The advantage there also, or the disadvantage of doing it with using an array, of course, is now you need to set aside space for an array. And you may not know how big that array is supposed to be ahead of time, so you might make it too big, or you might use something like an array list, which is constantly having to expand its array as it's accumulating results. So I'm trying to show you in this class that there's a different style of programming where you can just simply get a line of input, do something to that input, display the results, and then move on to the next line. And don't worry about anything that happened in the past. You don't need to store away the results of what you've done, because you can just simply display it on the screen, and the screen will keep a history of the stuff you've done. So there's that. So that can make your programs a lot more compact, because now there's no need to store away all the results in a separate array and then display that array at the end. I used to do an assignment where your job was to copy a file. Take an existing file and just make a copy of it into a new file. And if you did something like pull the contents of the source file into an array and then dump it out all at once into the destination file, your program could use a lot of memory if that source file was big. But the way that the copy command actually works is it reads in one line of the source file, and then writes out that one line, and then reads in one line, and writes out one line, and reads in one line, and writes out one line, and it never has to keep around any more than one line of the file. Makes your program really nice and short, because you don't have to do anything like manage memory. You just need to keep around one line of the file. And the real copy command doesn't even do that. It doesn't even care about lines. It just cares about blocks. So it reads in one block, like one 512 byte block, and then it writes out one block, and then reads in a block and writes out a block. That's all it does. So it's really fast, it's really short, and it knows nothing about the contents of the file. It just reads in 512 byte blocks and then writes out 512 byte blocks. That's it. So you never have to keep around any more than one block. So I just want to bring that up because I do see some students that are kind of going through the laborious process of creating arrays and storing stuff in arrays and then writing them out at the end when you don't have to do that. Now, I've been around long enough to where command line and terminal driven input and output is what I grew up with. That was all we had. And so that style of programming really comes naturally to me because that's the way we used to think about programs. But I can understand now that today's student might not think about programs in that way. They might think about storing the results in an array and then displaying that array as, all at once at the end. And you don't need to do that. For the majority of the programs we write in this class, you don't need to do that. Can we read the actual error returned by fopen and print it? So instead of printing couldn't open the file, could we display something like the file doesn't exist or the path is incorrect? Yes, we can. I will show that to you next week. Some additional library functions to call, but yes, you can. So we want to be able to display an error message other than just couldn't open the file. We might want to display what file couldn't be opened, and we might want to display also the reason why it couldn't be opened. So I'll show that to you next time. But in case you're curious about looking it up, it's done with a function called p-error, print error. Okay, so I think we have reached the end of today. We got through our list, which was where did my program crash? Command line arguments, memory allocation, and we did a little bit of files. So a little bit about all this stuff. So we will come back and we will revisit memory allocation over the next few weeks, and we will also revisit files. And we'll be using command line arguments again and again as the semester goes on, and also you'll want to know where did your program crash, because that'll be happening more and more often now. Okie doke. So, are we left with any questions for me?
I don't think so.
No, we're good. All right. Well, I hope you all have a great weekend. I know it's only Wednesday, but for this class, it's the end of the week. Take a look at the assignments. I know that to get back in sync, there's a fair amount to do, but remember the due dates are all really flexible, so get them in as soon as you can, and we will go from there. I had a couple of students say that they missed the week 7 or week 6 survey that they were supposed to do, and I will get back to those students and probably reopen that so that you can go and look at it again. But the next time when we get to about week 12, week 11 or week 12, then you should be paying attention for that so that you can do that survey when it comes out. Alrighty. Well, like I said, have a good weekend. Enjoy the weather, and I hope you, if you have any questions, then you can always send me an email, and I will talk to you later.
All right. Take care.
Take care. You too. Bye-bye.
Record.
Thanks for tuning in, YouTube folks. That looks like there was about 7 of you today, so it's always good to see you. You had some good questions, and we'll get to the answers to some of them next week. Just didn't have time today to talk about everything we wanted to, but we were going to talk about how do we get it to display the actual error messages, and what else was there? Oh, using reallocation for arrays. We'll be doing that as well. And then how do you get messages to appear like in bold? You know, you can do it. Obviously, you can do it because you can see it on the screen. Like some stuff is in bold and some stuff is in colors. What you have to do is look up something called the Antsy color codes. So on these old style terminals, which had color displays, it was really a cool thing back in the day to have things appear in color. But basically, most of these Antsy commands start with the escape character, which I believe is character number 27 on the ASCII chart, followed by a left bracket, followed by some additional characters. Excuse me. So let's see, where's colors? Oh, things like cursor up and cursor down. Like when you press the up and down and left and right arrows on your keyboard, your terminal program, the one you're using on your computer, is actually generating that escape, left bracket, and then the letter A, which means go up. And then when you hit like the back arrow key, it goes escape, left bracket, and then D. That's why sometimes in your programs, when you hit the arrow keys in an attempt to edit the line you're typing in, you see those characters come up. You see a bracket and a D. And that's because your terminal is actually sending those characters, sending that 4-byte sequence every time you hit one of those arrow keys. So if we go down here, here's colors. And so there's a bunch of colors that are defined, like color number 30 is black. Color number 31 is red. And the exact red you get depends upon, you know, so it's just color number 30. It's supposed to be red, but the exact red you get depends upon what terminal program you're using and what computer you're on. So, like, you know, in Windows, you'll get kind of like this dark red. Visual Studio Code, you'll get this kind of, you know, from like a vermilion. So you get a slightly different red each time. Same thing for green, different colors. Oh, you were asking about editor codes. You mean like the syntax highlighting? So you'd have to, I honestly, I don't know how those are done, but I'm sure there's some configuration file somewhere that tells it that when you see this pattern, you display it in this color or this, you know, with this effect applied to it. And I think it uses probably regular expressions. So you could write a regular expression that says, if I see something that's in all caps, like uppercase letter, uppercase letter, uppercase letter, uppercase letter, then apply this styling to it. I mean, I'm sure some quick Googling around will help us find that. Vim syntax highlighting. Make our own, customizing your own syntax files. Yeah, so you can do keyword matching, which does exact string matching. You can do regular expression matching. You can match regions of code, like, you know, for comment codes, like it starts with this and ends with this. So here, like do keyword matching for print, open, and if. But you might want to write a regular expression. Right? Here's one that matches numbers. So maybe that's got some information in there that you could use. And so usually the way it's triggered for something like Vim is it's based upon the file name extension. So if it sees this file name extension, then it will apply this styling to it. But you could maybe do that for text files. You could say, or C files. You could say, anytime I see a C file, I want to do this, apply this styling to it. Yeah, there's a lot of good stuff in here. How to install the files, how to activate them. Yeah, maybe that's what you need. And I do believe that even though this says it's for Vim or the VI editor, things like Visual Studio Code and pretty much any other editor also understands this. So even though it seems to be specifically for Vim, it probably also works for other editors as well. And other editors may have their own styling system, but I think pretty much they all understand this one. I'm guessing. It's speculation on my part, but I don't see why they wouldn't, because a lot of people use this. Okay, well, I've reached the end of today, and I will see you all on Monday, where we will talk more about files, and we'll get a chance to start talking about password cracking, which is going to be a really great part of the next few weeks. So we'll learn about hashing, how passwords get stored in databases, and then ultimately when a password file gets leaked out to the internet, how do people go and start cracking them? How do they go and find out what those passwords are? We're going to write programs to actually do that. So be really cool next, it's going to cover about 3 weeks or so. So yeah, have a good weekend, and I will see you next week. Take care, you all. Stay safe, get some sleep, have fun, and I'll see you next week. Bye-bye.